Hello, this is Dr. Michael Hassan, the Engineering Doctor, and this is lecture number 29, Introduction to Sequential Networks of Chapter 6, Flip-Flops of the course Digital Logic Design, or Digital Systems, or Digital Electronics. This slide is a disclaimer for you to read. I cite 3 references in Digital Logic Design, but there are many more available. Chapter 6 contents include sequential networks, synchronous versus asynchronous, Moore versus Mealy networks, memory elements, SR latch, the clock-SR flip-flop, JK flip-flop, T-type flip-flop, the D-type flip-flop, flip-flops characteristic equations, bi-state logic, modular latches and flip-flop, and VHDL design 5. Today we will talk about the introduction to sequential networks, and the next lecture we will start with the SR latch. What is a sequential network? A sequential network must have memory elements capable of storing data and may also have a combinational circuit. Now there are really some sequential networks without combinational circuit, but the general case is the sequential network will have a combinational circuit. A sequential network, also known as a finite state machine or FSM. And the reason behind this, if a network has n number of memory elements or flip-flops, the maximum number of states the network may have is 2 to the power n. For n number of flip-flops, the number of states will be 2 to the power n. For the 3 flip-flops, the network may have up to 8 states, and so on and so forth. Sequential networks find numerous applications in computer technology, telecommunications, digital signal processing, digital control, and so on and so forth. It's really an excellent tool used to control systems. It's very, very useful network. And this is what the course is all about, is designing sequential analysis and design of sequential network. You need a control circuit for an elevator. You can do it with a sequential network. So you can have a lot of control system designed with a single sequential network rather than with a microcomputer. I mean, there are a lot of control done by using microcontrollers unnecessarily. It's not needed. You can do it much cheaper, more efficient by a simple design of finite state machine. So sequential networks have really numerous applications, as we shall see. Synchronous and asynchronous network. Now, sequential switching network can be either synchronous or asynchronous. Asynchronous network utilizes an external clock to synchronize its operations. That is, the network output are defined at discrete instants of time. Synchronization ensures an orderly execution of the various operations and logical decisions to be made by the network. The memory elements used in asynchronous network are either latches or the flip-flop. So we have memory elements, and these memory elements are synchronized by a clock pulse CP. And the output of the memory elements, this is the output of the flip-flops, is from Q1 to QK. Now this will go to a combinational circuit, will come out as Q1 plus to QK plus. Now, what's the plus mean? This is called a present state, and those called the next state. Physically, the present state and the next state, they are the same. They come from the same source, from the same output. But the Q1 plus occur after the Q1 by instant of time. So if you Q1 took a place at T, Q1 plus will take place at T plus epsilon, or T plus 1, some people call it, okay? So this is what the difference between the present state and next state. So the next state is a stable state in the network, but the Qs are the same, came from the same physical output of flip-flop. Now, the combinational circuit would have a number of input, could be from x1 to xm, and a number of output could be from z1 to zn. You could have a single input and a single output. Okay. Now, what's asynchronous network? An asynchronous network, on the other hand, is a free-running network without any external clock, does not depend on an external clock. Hence, the network outputs depend on the order which its input signals change and can be affected at any instant of time. There are two main types of asynchronous network. Their classification depends on the type of memory elements used. In pulse mode, asynchronous network latches or level-sensitive memory elements are used. So there are two types, pulse mode, and there is a gate type asynchronous network with the propagation delay of the gates along with a single feedback or more in the network will make the network asynchronous network. Now, although asynchronous networks are faster than synchronous networks since they are not limited to the frequency of an external clock, their instability imposes many difficulties on the designer. Asynchronous network will be covered at the end of this course. State graph and state table, or state table and state graph. A convenient way of describing the behavior of a sequential system is the state table. The number of states is equal to 2 to the power k, where k is the number of memory elements of a flip-flop. The state graph is a graphical representation of the state table. We can get the state table from the state graph and vice versa. There are two synchronous networks, Moore and Mealy, the two most famous classification of synchronous network. It's Moore network and Mealy. In Moore network, the output Z is independent of the input X. So in the graph of the network, the state graph, as you see, each state will have a node, okay, which is a small circle, We will have the name of the state inside this node, the name of the state, okay, and in the Moore network, since the output independent does not depend on X, okay, so in the node we have the name of the state slash the value of the output, okay, and the author joining two stable states, the author will be labeled with the value of X. So this X will cause the change of the network from one state to another state, okay. So here, for instance, if the present state was A, the output is 0. So we'll have a node A and the output slash Z, 0. And if the network in state B, the output will be 1. If in state B, so the nodal circle will be B slash 1. If the network in state C, the output will be 1. So again, I have a small circle with the letter C slash 1 because Z is 1. If the network in state D, okay, the output will be 0. Again, I will have a small circle with the letter D inside and slash 0 because Z is 0. Now, what the network will do if X changes? If I am in a state A and the input X was 0, if the input X was 0, I will stay in state A. See, if A, so the next state, this is the present state, the next state will be also A. It means there is no change in the state. I'm staying in state A. So if X0, I will stay in XA. So on the arrow, we have the value, as you see here. The arrow joining two nodes, or maybe the same node, are labeled with X. So if X is 0, I'm staying in state A. However, if X is 1, I will go to state C, from A to C, okay, when X is equals to 1. Now, however, if I am in C, I can go in the sequence of the graph, or I can go in the sequence of the table. I can say if I am in state B and X is 0, I will go to A, If x is 1, I will go to C. If x is 1, I will go to C. Okay? And if I am in state C and x is 0, I will remain in C. See here, I remained in C. The arrow will take you back to C when x is 0. And if I'm in state C and x is 1, I will go to state D. Okay? And if I am in state D, I will remain in D if x is 0. And I will go to state B. I will go to state B if x is 1. Now, every state here must have two arrows because x will have two values, 0 and 1. So the outgoing arrows from the state must be 2. Must be 2. There's one outgoing if I am in state A, okay, A and C. So there are two arrows. One goes to A and one goes to C. However, if x was a 2-bit input, so x could be 0, 0, 0, 1, 1, 1, and 1, 0, and we'll have 4 arrows. Each state will have 4 arrows, 4 outgoing arrows. Okay? So again, the Moore network does not look super easy, does not look complicated at all. We will have z independent on the input x, and the node will carry the value, the name of the state, slash the value of z, and the arrows between two nodes, or sometimes the same node of the state, will be labeled with the value of x. Will be labeled with the value of x. And also we said every state will have two outgoing arrows because x may have two values, 0 or 1. How about Mealy network? In Mealy network, the output z depends on the value of the input x. The arrow joining two nodes are labeled with x slash z and the node labeled with the present state s. So the node we have circle, we have 4 states here. Because the table tells me 4 state, it means I have 2 memory elements, 2 flip-flops. Now I have state A, state B, state C, state D. Now why we put A, B, D, C? We do not put A, B, C, D. To avoid intersection of these arrows, okay? And when you draw the map, when you draw the graph, based on the sequence, the iterative sequence of the state, so you may have a very nice, neat drawing. But if you draw the state initially, you may have intersections, and you can rearrange the graph to look nice later on, okay? So here, again, z depends on the value of the input x, and the arrow joining two nodes are labeled with x slash z, and the node itself labeled with the present state s. So we have 4 states, A, B, C, and D will have 4 nodes, each one labeled with the present state. If I am in state A and x is 0, I will stay in A and the output is 0. So I will say I'll stay in A and the output is 0. So I will have x0 slash 0. X slash z or 0 slash 0. If I am in A and x is 1, the output will be 1, I will go to state C. See, so it is 1 slash 1, I will go to C. If I'm in state B and x is 0, the output is 1, and I will go to state A. So if I'm in B, 0 slash 1, I will go to A. If I am in B, and the input is 1, I will go to C and the output is 0. So present state B, x is 1, I will go to C and the output is 0. So B, I will go to C. Do you see here the arrow? I have 1 slash 0. X is 1 and Z is equals to 0. If I am in state C and x is 0, I will remain in C and the output is 1. So 0 slash 1. Okay, I will remain in C. If I am in C and x is 1, I will go to D and the output is 0. So I will go to D and 1 slash 0, 1 slash 0. If I am in state D, I will remain in D if x is 0 and the output is 0. So 0 slash 0, I will remain in D. If I am in D and x is 1, I will go to B and the output is 1. So I will go to B and the output is 1. So 1 slash 1. 1/1. And by this, we were able to really draw the state graph of Mealy Network. And again, Mealy Network has the number of nodes is equal to the number of states. Each node will have the present state. Each arrow will have x/z, which is the value of the input, slash the value of the output, because the output is input dependent, depends on the value of the input z. Now, these networks, sequential network uses latches or flip-flop. Both of them are memory element. But really, we would like to understand latch versus flip-flop. What's the difference between those two? A latch is a level-sensitive binary storage device implemented with a limited number of logic gates, often unsynchronized. The simplest latch is composed with two cross-coupled NAND or NOR gates. On the other hand, flip-flop is more sophisticated, clocked, age-triggered binary storage device widely used in practice, and often flip-flop is called master and slave. Has a master unit and a slave unit. They work together to give me a very stable flip-flop. There are four common latches and flip-flop. They are set reset or SL latch and flip-flop. Then there is trigger or T, and there is delay D, and there is the JK flip-flop. We will see there's a big problem with the set reset flip-flop. There is a state which we do not use, and this state has been solved with the JK flip-flop. So the JK flip-flop is a solution, is an upscale unit for the set reset flip-flop, and it is a great flip-flop, a JK flip-flop that we often use. Now, this is the last slide of lecture 29. And this is, as I said, the first lecture of chapter 6, which is, we'll talk about flip-flops in general. I would like to thank you so much for listening. Please subscribe, and hopefully to see you soon in the next lecture. To subscribe, please click on the blue circle. Sincerely, Dr. Hassan.